Hello students, welcome back to MKG Online Study, an e-learning platform. Today, we are finally entering the world of a real RTL design. Up till now, we have learned why RTL exists, how hardware thinks, how hardware remembers, why clock exists. But here is the question. How do engineers actually describe hardware behavior in Verilog? The answer is a construct called the always block. The This single construct is used in FPGA designs, CPU designs, GPU designs, and ASIC designs. In fact, if you open almost any real-world RTL project, you will find hundreds or even thousands of always blocks. By the end of this video, you will understand why. Always block describe hardware behavior. Foundation of a real hardware design is always block. Let's start with a simple observation. Whenever engineers build digital system, they need hardware to react to inputs, react to blockage, react to events. That's exactly what an always block does. Think of it as a mechanism that gives hardware behavior. Without always block, Verilog would be extremely limited. That's why they are considered one of the most important tools in RTL design. And this isn't just academic theory, this is how actual chips are returned. So, dear students, real chips are full of always blocks. Now, let's address the biggest misconception. The word always sounds dangerous. Many beginners see it and immediately think, oh, this must run forever. Reasonably assumption, but completely wrong. Looks like a software loop, but hardware is event driven, does not run continuously. Wait for trigger events. And always block does not continuously execute like a software loop. Instead, it waits. It remains idle until a specific event occurs. Only then does it execute. This difference is the key to understand Verilog. To understand this better, let's compare software and hardware. Software execute instructions one after another. The CPU follows a sequence, first instruction, second instruction, third instruction, and so on. Everything happens in order. Hardware doesn't work like that. Hardware is concurrent. Hardware reacts to signal changes. Multiple parts operate simultaneously. Instead of following instruction, hardware reacts to signal. And that's exactly why Verilog use event-driven constructs. Think hardware, not software. Let's focus on that phrase. Event-driven. Hardware doesn't constantly ask, did something happen? Did something happen? Instead, it waits efficiently. When an event occurs, it responds. This minor mirrors how real digital circuits operate. Signal changes, logic reacts, output updates. Signal changes trigger actions. Efficient simulation model. This event-driven model is one of the reasons Verilog can accurately represent hardware. Let's make this intuitive. Imagine you are sitting at home. Nobody rings the bell. Nothing happens. What do? Nothing. You continue sitting. The moment somebody rings the bell, doorbell rings. You stand up, you open the door, you react, then you wait again. This is exactly how and always block behaves. Wait, then react. Wait, react. This event is the doorbell. The response is the execution of the always block. Now let's decode the syntax. The symbol @ is extremely important. This symbol introduces event control. It is basically telling Verilog, wait for something to happen. The signals inside the brackets determine what that something is. This determines what that something is. Once a specified event occurs, the always block executes. Executes block when triggered. Then it returns to waiting block. Hardware listen for events. The signal inside the brackets from something called the sensitivity list. So this is sensitivity list. Think of it as a watch list. Hardware continuously monitors these signals. Whenever one of them changes, the always block wakes up. This concept is especially important in combinational logic because combination circuits must respond immediately to input changes. So the sensitivity list tells hardware exactly what it should pay attention to, defines what hardware listen to. Now, let's see a simple example, always @ A or B. Suppose the sensitivity list contains two signals A and B. Now hardware watches both. If A changes, the block executes. If B changes, the block executes. If neither changes, nothing happens. Any change, A or B, triggers block. Notice how efficient this is. The hardware only reacts when necessary. This is the essence of event-driven design. Input change, execution takes place. This type of always block is commonly used for combinational logic. Combinational logic has no memory. The output depends only on inputs, current inputs, we can say. The moment input changes, output must be recalculated. Example include AND gates, OR gates, multiplexer, decoders, arithmetic logic. In all these cases, immediate reaction is required. Act immediately. Pure combinational behavior. So, dear students, do remember always block is used for pure combinational logic. Assign versus always. At this point, you might wonder why not simply use assign statement? Good question. But both assign and always block can model combinational logic. For simple equations, assign is often clear and it is compact. But real design quickly become more complicated. Always handles complex logic. When logic grows larger, always block becomes much easier to manage. That's why engineers frequently prefer always statement. Different tools, same goals. Imagine designing a control unit. You need if else statement, case statement, multiple conditions, complex branching. Use assign statement becomes messy. Always blocks solve the problem elegantly. They allow hardware designer to express complex behavior in a structured way and does complex designs easily in a structured way. That's one of the reasons they are everywhere in RTL scales better in RTL. Now we are entering the really exciting part. So far we have discussed combinational logic, but what if hardware needs memory? That's where sequential logic comes in. Sequential logic depends not only on current inputs, but also on previous state. They stores previous state's output. It stores information. And most of the common way to build it is using clock triggered always block, triggered by clock gauge. Clock introduces memory. This line is one of the most famous statement in digital design. Always at the rate posedge clock. Whenever the clock transitions from 0 to 1, the block execute not continuously, not randomly, only on the rising edge. This creates synchronization. And synchronization is the foundation of modern computing. Most common RTL design use posedge, that is rising edge. Let's examine a simple register. Input data arrives on signal D. Store value appears on Q. At every rising edge, the value of D is captured and stored in Q. That's memory, that's register. And that's how digital system remember information. Register is the basic building block. This is one of the most important comparison in Verilog, combinational versus sequential. Combinational logic, no memory. Sequential logic has memory. Respond to clock events, understanding the distinction is absolutely critical. Many beginners' mistakes come from confusing these two concepts. Combinational, no memory, sequential, has memory. Now let's connect this to the real world. GPUs use always block, NVIDIA GPUs use always block, FPGA use always block, ASICs use always block. Whether you are building a tiny controller or a billion transistor processor, the same principle, same RTL principles everywhere use always block. That's why mastering always block is such a valuable skill. Now let's introduce a mystery. Look at these operators: equals and less than equals. Equals and less than equals. They seem almost identical, but in Verilog they behave very differently. Look similar but behave differently. One is called blocking assignment, the other is called non-blocking assignment. Choosing the wrong one can create serious bug. Learn the difference. Blocking assignment and non-blocking assignment. Before we finish, remember these patterns. When, when you see always at the rate A comma B combinational, think combinational logic. When you see always at the rate posedge comma clock, sequential. Think sequential logic. These patterns appear repeatedly in industrial RTL. Memorize them. They will save you a lot of confusion. Do remember, without clock, combinational; with clock, sequential. We have solved one mystery today. What always block are, but another mystery remains. Why does Verilog has two assignment operators? Which one should be used in register? Which one should be used in combinational logic? And why do experienced FPGA engineers care so much about this topic? That's exactly what we will uncover in the next lecture. Blocking versus non-blocking assignment. Why Verilog has two assignment operator? Race conditions and simulation mismatches. RTL best practices and industry guidelines. This version is now, that is, this video is now towards its end. So, dear children, do remember why we have used this always block. What we have learned today, always block in combinational logic, how to use in sequential logic, what the two blocking versus non-blocking assignment operators. You are building the foundation of real digital system design. Thank you for learning with us. Thank you for supporting you. Your supporting means lot to me. Keep practicing, keep building, and keep innovating. See you in the next lecture. Thanks for watching.